Hello everyone, thank you for taking time to look at this particular video. This will be a series of videos on differentiation rules. We're going to start off with the most basic ones, the four that I have listed here. We're going to go over those quickly and then do some examples of those. So the first rule that we have is the derivative of any constant. And so the derivative of any constant is zero. This is mimicking taking the derivative or find the horizontal tangent lines of, well, the slopes of the tangent lines rather, of a horizontal line. And so, of course, we know that slope of a horizontal line is always zero, and therefore the slopes of the tangent lines on that particular function will always be zero as well. So that's why the answer to derivative of any constant is zero. The next just tells us that if we have a function that is a non-zero multiple of another function, we can just pull out the constant here. Okay. The next one tells us if we have the sum or difference of two functions and we can take the derivative of those two functions separately, then we can go ahead and do that and then either add or take the difference to get the answer. And then lastly, which is probably one of the more important ones here for this particular session, is the power rule. And so this tells us that whenever we're dealing with something raised to a power, whether it's a nice integer number or fractional exponent, we can deal with it just by saying we want a derivative of it, take n, multiply to the beginning of the function, and then subtract 1 from the exponent. So we're going to do a few examples to try to get using these particular rules under our belt. So the first one that we'll do is taking the derivative of 50 with respect to x. And so we know that since this is a constant, it goes along with this rule. So the answer is what? Yep, that's right. It's 0. Okay. So pretty simple, right? Okay. Let's move on to the next one here. So let's say we have a polynomial that looks as follows. And I'm going to write this a little bigger. So let's say we have this particular polynomial function. So 2x to the fifth minus 1/2 x to the fourth minus 3x squared plus square root of 2x minus 3. So as you can see, this is a polynomial function, and a polynomial function is just a sum of power functions. So if we were wanting to take the derivative of this, we would start off with the first term. Here, this is a constant. So we write the 2 out according to this rule. And then here we see that we have x to the fifth. So we would bring the 5 out and then do 5 minus 1. And 5 minus 1 is what? Right, that's 4. Move to the next term. Minus 1/2 because that's our constant. And here we have x to the fourth. So we just move the 4 over. And x to the 4 minus 1 is 3. Next example, next term will be -3. Bring the 2 over. And then 2 minus 1 is just 1. And of course, we don't have to write the understood 1 there. Plus, our constant is square root of 2. And of course, for this one, this is understood to be x raised to the 1. So we bring the 1 over, and x to the 1 minus 1 is 0. And then, of course, the derivative of any constant is what? That's right, it's 0. And so now from this stage, we just clean it up. So that will be 10x to the fourth. 1/2 times 2 is 1/2 times 4 is 2. X cubed minus 6x. And then we have square root of 2 here. And we know that anything raised to the 0 power is equal to 1. So that would just be square root of 2 times 1, which is just square root of 2. And then, of course, our minus 0 at the end. So we don't need to write that. And so if we were doing a derivative of this particular polynomial, this is what it would be. Okay. All right. So we're going to erase this now, and then we're going to do a few more examples where we see some negative and or fractional exponents. All right, so next we're going to do this particular problem. And as you see, we have something here that looks a little different. But if we can rewrite what g of x is, we can get it into a form to where we can use all these particular differentiation rules. So to start off, we see here, g of x is 9 over x raised to the 1/6 power, okay? And so we could rewrite this to be 9 times x raised to the negative 1/6 power minus, and then we can write this as 3 times x raised to the negative 2/7 power. And so we know that from our exponential rules that say whenever we have something raised to a negative exponent, we can rewrite it this way. So that's where that comes from. So now continuing on, if we go here, this term follows the power rule. So we'll say 9 times negative 1/6 x, and then negative 1/6 minus 1. Then we have our negative 3 times a negative 2/7 x, and then that's raised to the negative 2/7 minus 1 as well. Okay, I'll go ahead and erase this. And so now from this point, it's just a matter of cleaning everything up to make it look nice. So here we know that this could be a negative 9 over 6 x raised to the, we know that this 1 can be written as 6 over 6. So now that is a negative 7 over 6. And of course here we have a negative times a negative, which is a positive, 3 over 1. So when we multiply numerator with numerator, that will be 6. Denominator with denominator, that will be 7. And again, here we know that we can change this 1 to 7 over 7, which gives us x raised to the negative 9 over 7. And so in the negative exponent form, this is what the derivative would be. Since we were given our original function with positive exponents, we want to rewrite this with positive exponents as well, okay? So here we want to go ahead and simplify this before we do that. So we know that 3 times 3 is 9, 3 times 2 is 6. So both of these have a factor of 3. So if we reduce, that would be 3 over 2. So we'll come or write this, and then after that, we'll put everything in terms of positive exponents now. And so that is what our answer would be if we were to write everything with positive exponents. Have one other example, and then after that, we'll go ahead and move on to the second part of this particular series. All right, so again, we have a function where we have some positive exponents, but of course they're in the denominator. And of course we have here a fourth root. So we want to rearrange the way that that looks so that we can try to use these particular rules here, in particular the power function. So if we want to find the derivative to this, and of course another way that I could write that would be as d over dw of h of w.
Can't see that.
Okay. So we can write it that way as well. So here, start off with our h of w. We're going to write this, but move the w to the fourth up and make a negative exponent on it. And here we know that the fourth root of w is the same as w raised to the 1/4 power. And so if you've forgotten about the rules for that, we know that this is how we take an nth root and write it as a fractional exponent. So from this point, we can now take the derivative, and you can see, once again, all we have here is the power rule to use. So h prime of w, which is a derivative, our non-zero constant 9/5. We bring the 4 over, multiply, and then we subtract 1 from the exponent. And next time we take our positive 1/4 and then subtract 1 from the exponent. So with this stage, we go ahead and clean up. So here, there's nothing that can simplify, so we're just going to multiply numerator with numerator and denominator with denominator. So this would be negative 36 over 5, w raised to the negative 5. And then our next term, we have 7 over 4, w raised to the, here we know that we can change the 1 to 4 over 4. And now we have w raised to the negative 5/4. And so now from here, just like how we did in the last example, we were given positive exponents for the function to start off with, so that's how we want to leave it. So this is how we would rewrite our first term. And of course, our second term was given in terms of a fourth root, or an nth root rather. So we'll do the same here. And so that's what it would look like if we changed the w raised to the negative 5/4 back into a fourth root, or an nth root rather. All right, go ahead, stop.